In this video, we're going to talk about the first two different types of traveling waves called transverse waves and longitudinal waves. I'm sure that you were introduced in grade 9. The first wave we've already kind of introduced with that rope being moved up and down. As you can see over here, that's what this lady's doing, except instead of a rope, this is a spring, but she's vibrating it up and down, sending a pulse, a wave pulse down. So the frequency of vibration is enough that you're starting to see a proper waveform here. So the distance between here and here would be your wavelength, okay? And here's just another diagram of a hand moving a string. And what you can see is that the displacement causing the wave is perpendicular to the movement of the wave. The wave propagates horizontally, but the displacement causing it is vertical. So the definition of a transverse wave is that the displacement causing the disturbance is at right angles to the direction of energy transfer. If that's the case, then what you get is a transverse wave. Okay, and that's common in strings. It's common in many different types of waves, mechanical waves that we generate by a vibrating object. Okay, so what kind of calculations can you do with this? Well, standard, you can calculate the speed of it. Okay, so if I was standing here and I timed, if it was going slow enough and I timed the time that it would take for that pulse to move from here to here, the distance, I can just take the distance divided by time, and that would give me the speed. Or if I calculated how many waves passed me in a second, that's the frequency, and I knew the wavelength, I can multiply those two things together and get the speed, just like we did in the last one. Now for higher level students, there's a lot more that we can do. Okay, so standard level, you just have to be able to answer this wave equation type of situation here and calculate the speed of the wave and whatnot. But for higher level, we look at transverse waves as the individual particles in that string causing the wave. Okay, so these particles are moving up and down. They're oscillating about an equilibrium position. Okay, just like we did for simple harmonic motion. So all the equations we looked at in simple harmonic motion apply. All right, if I know the period of that wave or the frequency, I can then get the angular frequency of that oscillation motion, and I'll be able to calculate for every particle A, B, C, or D, I'd be able to calculate where that particle will be in a certain moment in time. So if I started the wave motion here, that particle is at its amplitude. I would say that this is a cosine function, and I'd be able to apply all the simple harmonic motion formulas to be able to calculate the acceleration of that particle at that moment, the velocity of the particle at that moment, where that particle will be in 3 seconds, the displacement. Will it be here? Will it be here? Will it be here? Okay, and you'll need to be able to graph that. So for HL, you'll have to apply everything we did in simple harmonic motion when we look at waves. Okay, all right, another type of wave, or here, sorry, no, these are the graphs of waves. So I also, in addition to that, we have to be able to mine information from different types of graphs. In waves, you're always given two different types of graphs. Here's the change in the amplitude on the y-axis and the distance that wave has traveled. So imagine this is a snapshot of a surface of a pond over time. So this is a 10-meter snapshot. So if I took a snapshot at time point 0, this is what the waves look like. And then if I took another snapshot, I might see that the pattern changes. I'd be able to interpret some information from that. So that's like a distance in the y-axis over distance in the x-axis graph, okay? What kind of information can you get from that? Well, for SL, the only thing you're going to be able to get is things like the wavelength, the distance between the peaks. And that looks like the wavelength here is about 2 meters is your wavelength, okay? For HL, you'd be able to then get the amplitude, okay? So from this amplitude and other factors there, I'd be able to then apply the simple harmonic motion formulas to be able to do a lot more different calculations that you'll see later on in your dot points, okay? Then the next graph that needs to accompany this is some information about time. Okay, so here's the change in the y-axis, the amplitude of that wave over time. Okay, I can see in this snapshot, the period of that wave is roughly, let's say 7 seconds, okay? So the period is, yeah, somewhere around 7 seconds, maybe a little bit more. Okay, so what can I do with that? Well, I can use both those pieces of information to calculate the speed of the wave. Okay, or the other equation, which would be the speed of the wave Okay, so the speed of that wave is going to be 2 meters divided by 7 seconds. Okay. All right, so longitudinal waves are a little bit different. And examples of longitudinal waves that we definitely know about is sound. Okay, the voice that you're hearing from me is generated by my vocal cords pushing and pulling on air particles. Okay, now the difference between a transverse wave and a longitudinal wave is that the displacement causing the disturbance is parallel to the direction of energy transfer. So if that wave and energy is going in this direction, that disturbance also has to be moving in that same direction. So here you got a hand that's attached to a spring, okay? And that hand squeezes that spring in. It's going to squeeze the little rings of the spring together, and then it pulls out and it stretches them apart. And what you see is that the squeezed rings together will be kind of moving as a pulse back and forth. Like, I'm sure you've played with springs and you've sent these pulses back and forth. You can try it at home if you have a spring. Okay, so if you squeeze it, you'll send this squeezed pulse down the spring and it'll reflect back. Okay, so I can compress the spring, and if I pull it back, I can stretch the spring out, and then you have two different types of forms. Just like we had crests and troughs in a longitudinal wave, when you make a squeezed portion of it, that's called a compression. That's an area of higher pressure. And when I push and pull, okay, and stretch it out, you create a rarefaction. So the combination of a rarefaction and a compression is a full wave of a longitudinal wave. There's a zone of compression and a zone of rarefaction, okay? So the distance between here and here would be the wavelength, okay, of a longitudinal wave. Okay, so I said sound is a good example. I can make longitudinal waves in water if I push and pull water particles. Okay, so it's usually, you need a medium to transmit a longitudinal wave. Okay, so here's an example of sound, how it propagates. Okay, look at this tuning fork over here. It's vibrating. As it's vibrating, imagine it's a speaker. It's pushing, it's going back and forth, back and forth. So when it pushes, it creates a zone of pressure. Okay, and then this zone here where the particles are less dense is a rarefaction. It's a zone of low pressure where everything got stretched out. And these pressure zones move down that tube. Okay, your ear has an eardrum on there that can feel that pressure. The pressure pushes the eardrum in, the zone of low pressure pulls it back out, and it vibrates with a frequency that sends signals into your inner ear so that you can detect frequencies of sound based on changes in pressure. Okay, so here you'll have an example of where it's a graph of pressure over time. Okay, high pressure, which means it's a compression, low pressure, which means it's a rarefaction, and so on and so on and so on. So the distance between, or the time difference between here and here would be my period for that sound wave. Okay, likewise, I can generate this mechanically with my hand. If I push air and I pull, I'll create a longitudinal wave in air where I create a zone of pressure and a zone of zero pressure. That's a compression and that's a rarefaction. Okay, and I can do that just with my hand, or I can create a speaker that's moving in and out at a higher frequency to generate that. Okay, so with longitudinal waves, they also follow the wave equation. And what's important is the speed of sound in air at room temperature is about 340 meters per second. That's an important characteristic to know. So if I have the speed of sound at 340 meters per second and my flute is playing 254 hertz, what would the wavelength be? Okay, well, in that case, 340 meters per second divided by 254 hertz would be my wavelength. Okay, and then if I did that division, then you'd see the wavelength is a little bit more than 1 meter. All right, now 254 hertz is around middle C on a piano. All right, interpreting graphs of longitudinal waves, same thing. The first graph that you're going to get is displacement away from the source and displacement towards the source. Remember, this isn't like a wave that's moving up and down. This is a wave that's moving parallel with the direction of propagation of energy. Okay, that's what it says right over here. So that displacement is in the same direction. So that would be moving away from the speaker. Okay, if it's positive, the displacement is away from the speaker. Okay, if it's negative, the displacement is towards the speaker. Okay, so everything positive, the direction is away from the speaker. Everything negative, it's towards the speaker. The motion is towards the speaker. Okay, so I'm just drawing this direction of motion of those particles in the medium. Okay, so if I look over here, see where I'm pushing and those two zones are coming together, that area here would be a compression. So that's an area of high pressure. Here they're being pulled apart, and that would be a rarefaction. Okay, that's a lower pressure zone. Okay, so that you'd have high pressure here and low pressure here. Okay, if I put this wave into a tube and somehow made that wave stand still, I would see dust moving to the areas where there's zero pressure. Okay, so dust would start to move over here. You'd see a lot of dust moving away from the compressions and collecting at the rarefactions. Okay, and then this graph is your classic time graph. So displacement in the y, so that would be in the right to the left, and t is on the bottom here, so this would tell you your period. Okay, so from this I know my period. Okay, I would know my wavelength, okay, by the distance. If this is distance from the source, this graph would tell me my wavelength. From here to here is my wavelength, or from compression to compression is my wavelength. So wavelength divided by the period of the wave is going to give me the speed. All right, and that's how we interpret the graphs and analyze longitudinal and transverse waves. Okay, the next video is just going to talk about light and electromagnetic waves, and then we're on to doing some interesting calculations and learning about the phenomena that waves have.